So jumping into the scalar product of two vectors, this is where vectors starts getting a little bit more complex in that we're starting to look at the product of two vectors. So I don't want you to get confused with previously we've multiplied a vector by a scalar, which is not the same here. We're looking at multiplying two different vectors. So there are two different types of multiplication involving two vectors. So we can multiply two vectors together two different ways. The first one, which we're going to do now, is called the scalar product of two vectors. And it results in a scalar answer, which means that when we multiply these things together, we get just a constant almost out, like just a solo number. It has the notation a dot b, and we actually call, most areas of maths and physics call this the dot product. The other one is called the vector product or cross product of two vectors, and it results in a vector answer. We don't do this in year 11. It has the notation a cross b. So let's jump into it. So the scalar product or the dot product or the inner product of two vectors. So if we've got our two vectors, we've got a here, a1 and a2 are our two different elements, and b, b1, b2. Then if we do the dot product of these, a dot b, what we do is we actually multiply. Now, it'll be easier with a highlighter. We multiply the top elements together or the corresponding elements, and then the second ones together, and we add them together in that space. So it's actually a pretty simple operation. Let's do the example, then we'll come back up to the algebraic properties here. So this here means if we're going to look at the dot product of p and q, all we do here is we go, well, p dot q is going to equal p has 2 in its first element, and it's going to be 2 times 1, and then plus in the y component of these vectors, we've got 3 and 4. We're going to multiply them together, 3 and 4. And so our dot product here is 2 plus 12, and it equals 14. Really easy here. So that's the dot product there. Just remember the corresponding elements. Now, algebraic properties of the scalar product. A dot b is the same as b dot a. So what this is actually looking at is sometimes we have operations with numbers that we can do, similar to, we've talked about this before, in that you can't divide a vector, so we multiply by a scalar. We've got other strategies here. So these are some of the rules we can use, and we can use these in the algebra we do for vectors. So order's not important when we do the dot product. If we have the dot product of a dot a, it's equal to the length of a squared. Now, this actually makes more sense when we think about what the length of a looks like, which is the square root of a1 squared plus a2 squared. And if we square all that, the squares vanish, and we actually end up with a1 times a1 plus a2 times a2, which is the dot product of a there. This is like a distributive law, so it's the distributive property. If we add these two vectors together, because we do brackets first, and then we do the dot product, it's actually the same as if we did the a dot b and a dot c. Okay, so sometimes this can be a little bit easier. And then this is like a FOIL expansion here. If we have two vectors added together, dot product with two vectors added together, we can do an expansion. Fronts, a times a dot c, a dot d, which is the outer inners, b dot c, and b dot d there. All right, now just an example of a proof here. So for two vectors v and w, prove that v dot w equals w dot v. So when we do a proof like this, we're looking to break these into vectors. So let's just go, well, v is going to equal v1, v2. So these numbers in here, they're just numbers. Even though I'm using letters, they're pretty much just saying, well, we're going to use this as a general form. So w1, w2. So then we go, well, the dot product of v dot w is going to equal v1 w1 plus v2 w2. So that's the dot product of v dot w. Now, you've got to remember here that these are just numbers. So this would be like, in this v vector, this could just be like a 3, and this could be like a 2. And so the order of them is not actually important. So because of these aren't vectors, we can actually go, well, that's the same as WV1 plus W2 V2. So I've swapped the constants here. And now if you consider that, well, that is actually going to be the same as it's the W component first times with the V component, and then the W component times the V component, which means this is the same as the W vector dot product the V vector. All right, and that's it for this section. Really short section here, so whip through it, please.